All right, let's talk chromatography. You've been there, right? You run a column, and sometimes you get this beautiful, clean result. And other times, it's just a blurry, useless mess. So what gives? Well, the secrets are actually hidden in two really fundamental theories. So let's dive in and unpack how this whole separation thing really works.
I mean, this is the core question for anyone running a column, isn't it? It's the difference between having clear, reliable data and just a bunch of confusion. And the answer? It really lies in understanding what's actually happening to those tiny molecules as they travel down the column.
Okay, so if you want that perfect separation, we really need to master three key things. First, there's efficiency. That's what gives us those nice sharp peaks. Then you've got speed, because, time is always a factor in the lab. And finally, resolution, which is just our ability to clearly tell one compound apart from another. And, lucky for us, there are two key theories that help us understand and, more importantly, control all of this.
All right, so first up is what we call the plate theory. Now I want you to think of this as our starting point. It's a simple, pretty elegant model that just helps us picture what a perfect, ideal separation would even look like.
So the core idea here is something called the theoretical plate. And let me be super clear, this is not a real physical plate inside your column. Nope, it's a conceptual slice. It's a hypothetical zone. Just imagine for a second that your sample molecules could just pause and perfectly distribute themselves between the mobile phase and the stationary phase. That little zone of perfect equilibrium, that's what we call one theoretical plate.
Okay, so here's the crucial point, and a great way to visualize it. Picture the entire column as a really long staircase. Each and every step on that staircase is one of these theoretical plates. So it stands to reason, right? The more steps you can cram into that staircase, the more chances the molecules have to separate from each other. And that leads to a much cleaner, much sharper result.
And what's really cool is that the staircase idea isn't just a nice visual. We can actually put numbers to it and quantify the efficiency. Plate theory gives us two key values that tell us exactly how good our column is performing. Let's check them out. First up, we've got H, or HETP. That stands for height equivalent to a theoretical plate. And if we stick with our staircase analogy, this is basically the height of a single step. The formula is super simple, just the total length of the column L divided by N, the number of plates. And here's the key. A smaller H value is what you want. It means your steps are shorter and smaller, so you can pack way more of them into the same column, and that means a better separation. And that, of course, brings us to N, the total number of theoretical plates in the column. The great thing is we can calculate this number directly from the chromatogram you just ran. It's basically a function of the retention time and the peak width. And unlike H, for N, bigger is better. A higher N value means a more efficient column, and that's what gives us those beautiful, sharp peaks we're all after.
Okay, this all sounds great, doesn't it? A nice, tidy staircase with perfect little equilibrium steps. But let's get real for a second. Is the world ever that perfect? Does anything in chemistry, or physics for that matter, ever behave in such an orderly way? No way. The reality is that molecules are messy. They're constantly moving, bumping into each other, and just naturally spreading out.
And that is exactly where our second theory comes into play, rate theory. This is what takes us from that clean, idealized world of perfect plates and drops us right into the dynamic, sometimes chaotic, but much more realistic world of what's actually happening inside that column. So how does rate theory actually build on plate theory? Well, think about it like this. Plate theory imagines this perfect, static equilibrium on each step. Rate theory says, hold on. In the real world, things are always moving, so you never truly reach that perfect equilibrium. And maybe most importantly, plate theory completely ignores how fast things are moving. Rate theory, on the other hand, shows us that the flow rate is actually one of the most critical factors we have control over.
And at the very heart of rate theory is this, the Van Deemter equation. Now I know it might look a little intimidating at first, but it is absolutely brilliant. What it does is connect H, our plate height that we talked about, directly to U, which is just the speed of the mobile phase. It's the equation that tells us exactly why our peaks spread out and get broader.
So this equation basically breaks down peak broadening into three main culprits. First, you've got the A term, that's eddy diffusion. Just imagine some molecules taking the scenic route through the column packing, while others find a super fast shortcut. That difference in path length spreads them out. Then there's the B term, longitudinal diffusion. This is just basic physics, Molecules will always naturally spread out from a concentrated area. And finally, the C term, mass transfer. This is all about the time it takes for molecules to move into and out of the stationary phase. Some get a little stuck. And all three of these things are happening at once, working together to make our nice, tight peaks, well, wider and messier.
And here's where it all comes together visually. If you actually plot the Van Demeter equation with plate height, h, on the vertical axis and flow rate, u, on the horizontal, you get this classic U-shaped curve. And our job as analysts is to find that sweet spot. See it? It's right there at the very bottom of the U. That point is the optimal flow rate to get the smallest plate height, and therefore the sharpest, most efficient peaks possible.
Yeah, this really sums it up perfectly. The Van Demeter equation proves that there is an optimal speed for your mobile phase. A speed where all that band broadening is at its absolute minimum. It's not about going as fast as you can or super slow. It's about finding that Goldilocks speed. Not too fast, not too slow, but just right for the sharpest, most efficient separation you can get.
Okay, so we've got these two really powerful theories, plate theory and rate theory. That's great, but how does this actually help you in the lab on a Tuesday afternoon trying to get excellent results? Let's connect the dots.
Well, we do this using a set of checks called system suitability parameters. Honestly, you can just think of it as a report card for your chromatography run. And look, right at the top of the list is N, the number of theoretical plates, which comes straight from plate theory. But to get the whole story, we also look at things like resolution. How well separated are our peaks, really? And tailing factor, which tells us if our peaks are nice and symmetrical. All of these together give us a complete picture of how good our separation really is.
Now this is what we want to avoid at all costs. This is low resolution. See how the peaks are just bleeding into each other? There's no clear separation. You can't possibly quantify either of these compounds accurately because you have no idea where one peak ends and the next one begins. For all practical purposes, this is a failed separation.
And this is the goal. This is what we are all aiming for. Look at that. You've got sharp, symmetrical peaks with tons of clean baseline between them. That, my friends, is high resolution. It's clean, it's quantifiable, and it's the beautiful result you get when you actually understand and apply the theories we've been talking about.
So, to bring this all home, it's really important to see that these two theories aren't fighting each other. They're a team. They're complementary. Plate theory tells you what a great separation looks like. That's your high N value. Then, rate theory comes in and tells you how to achieve it by giving you the roadmap to optimize your flow rate and get that H value as low as possible.
So listen, the next time you're in the lab setting up a run, please don't just pick a flow rate out of thin air. Think about that Van Demeter curve. Think about the trade-offs you're making between speed and efficiency. Because now you know the theory. And that's the knowledge that separates the good chromatographies from the truly great ones.